This is ITKM for 560 for logistic regression. Let's get started. You should have seen the videos, the theoretical videos 1 and 2 before going through this video. It'll be a lot easier to understand what's going on. So that said, let's start loading our packages. Read art so I can load my data. Tidyverse so I can manipulate my data. Loading my data. And now I'm going to create this data set called affairs LR, as in logistic regression. So I'm going to run this, but I'm going to tell you what I did. I inserted into this new object the data set affairs. Then I created new variables. The first variable is random, the other one is cheater, the other one is occupation. Random is basically the number of observations that I have, 601, which is creating a uniform random distribution of numbers so I can split the data later into training and validation. I created the variable cheater. So we have the number of affairs, or the number of months within a year that you've had affairs, but we're transforming it to a 0-1 variable, meaning yes or no. So are you a cheater or not? And I've defined cheater saying if else. So my condition is if you've had more than 0 affairs, I am labeling you a cheater. If not, you're not a cheater. Occupation is equal to, as character, the same variable occupation. Occupation is a variable that it goes through 1 through 7, and it's numeric. But we know that these are categories. So I'm going to label it as character. The model for the algorithm for logistic regression doesn't care if it's a character or if it's a factor. But it has to be one or the other, so it'll know it's a category. Then I am going to select variables, which I'm doing it as with a minus sign in front. I'm taking away the variable affairs because I'm not going to be using affairs. Neither I'm not going to be predicting affairs, nor am I going to use it to predict. I have created my new dependent variable cheater here. So let's take a quick look at it. Okay, I have my random number, cheater 0, or all the way up to the cheaters here on the bottom, 1 for the cheaters. Back to here, I'm going to do my summary here, and basically I have 24.96% of the data are cheaters, or rather a quarter of them. From previous classes, we know this already. We have our random variable that the average is 0.51, the median is meaning the middle number is 0.54, and here we have occupation is just saying it's a character, so grade is not a number. So let's split our data to training and validation, where basically I am splitting the data 70% for training. So if the random number is less than 0.7, you're going to the training data set, and if it's greater than 0.7, meaning 30% of the data, you're going to the validation data set. And I also take out the variable random because I am not going to use that to predict. Okay, moving on. This is how we create a logistic regression model. I create a new object, which I have called it fit LR1. I am using the GLM function, which stands for generalized linear models. And I am predicting cheater, and I'm predicting cheater with all the other variables. I am using the training dataset, the train LR dataset, and this is very important, so it becomes a logistic regression model. I'm saying the family is the binomial family, and the link is the logit. If you've watched the theoretical videos, you'll understand what I mean by the logit. Okay, we need this to later be able to create the predicted values for cheater or not cheater. Okay, so let's run this. Okay, and let's take a look at that model. So there's a few things that I want to show. We have a few variables that seem to be significant and other ones that are not. And we'd like to do maybe perhaps some automatic selection here. Okay, there is, so for that, there's not really an automatic selection, but rather we're going to use this over here to be able to say which variables should I use. Let's see what the outcome is here. And it's telling me I should just use, even though there were others that were significant, it's saying that I should just use years married, religiousness, and rating. This is above, children is above the 0.05 level. That's my cutoff point. If it's 0.051, I'm not using it. If it's 0.05 or less, I will be. It is more than 0.05. This has 601 observations, the entire data set. What I'm using to create the model is 406 observations. I would say safely, if your data set has 10,000 observations or more, you should not use the 0.05 as your cutoff point. I would use 0.01, even with 5,000 observations, perhaps the 0.01. These are judgment calls, but I'm telling you what my judgment would be. So, years married, religiousness, and rating. So I'm creating my model again using fit_lr2 as my object where I'm going to save it. So I'm predicting cheater with years married plus rating plus religiousness. I'm using the training data set and again the same family binomial with the link is equal to logic. Let's run this, run our summary, and here we have it. Obviously they're all significant, and we can do our ANOVA to do a double check. Yes, they're all significant at 0.05 or less, so I'm good. There is something else that I'd like to review now. To know that you've achieved a better model than the previous model, because we have the model with LR1, fit LR1, and fit LR2. Let's do the summary of fit LR1 again. I want you to take a look at something. So this is a model that uses everything, whether significant or not. Look at this value here, the AIC, the Aikikian Information Criterion. It says 403.55. That number in itself means nothing for you. What you are looking for is when you create another model, the number you're looking for is something smaller. So let's do this one. So the summary of fit LR2, the AIC number should be less than 403.55. Let's take a look. It is 404.18. So we have a slight, let us say, difference between 403.55, which is less, and 404.18. Now, it's a judgment call. Which model do you want to use? Well, the reality is that I personally, even though this is slightly higher, I would prefer to use this one. And I'm going to tell you guys why. Because the difference between a 404.18 and 403.55 is very small. Now, if we're just basing it off the numbers, I would use the first model. However, their first model uses all the variables, while the second model uses just 3 variables. In modeling, we prefer something that's called parsimony. Parsimony means being frugal with our terms. We want to use less predictors rather than more. We want to use all the predictors that are significant. We just don't want to use ones that are not. So I'm just going to, for now, I'm just going to stick with the second one, okay, as the one that I like to use. That said, let's see how we create our scoring. So if we want to score and we want to test, start seeing how good our model is, and this is where we're going to review this and stop, is that we are going to use the validation data set, and I'm going to create a variable called the logic, meaning it's not going to be our prediction yet, but it's almost there. So I'm going to use the function predictGLM. I'm going to use my second model, the one that I choose, and the data set, again, val_lr. If I run this and take a look at val_lr, I can see that I have created the logic. Now, it is not the predicted value yet. Okay? Again, the model produces the logic. the predicted value, which is going to be a number between 0 and 1, which is what logistic regression is used for, to predict a category. And it doesn't give you the category whether it is a 0 or a 1, but it'll give you a probability. Okay? A probability is something between 0 and 1. These are not numbers between 0 and 1. To do that, we need to take the variable we just created, the logit, and we need to apply this formula. This formula has been in your theoretical videos. This is what you will have seen. So I'm creating my variable predicted cheater. I run this, and now I can actually see this here. Now this is giving me a value of the likelihood of this person being a cheater is 11%. The probability of this person being a cheater is 0.07. The probability of this person being a cheater is 37%. Okay? And we will stop here, and in our next video, we will evaluate how good this model is.